All right. Hello, everyone, and welcome back to our second session of the large-scale systems, and with a focus on buildings and infrastructure today for ICE. And if you weren't here before, we had a great session last time, but we got another great one planned here as well. In particular, this topic is going to focus a bit more on buildings, circular economy, and life cycle assessment. So we have a whole bunch of speakers planned. Our first speaker was so popular that we put him in two sessions at the same time. Peng, as you can see here. So even though it shows Fernanda as being the first one in the program, Peng's going to go first. Fernanda will go third. And so with that, Peng, I'll turn it over to you for your 15 minutes presentation, and then we'll be glad to open up for questions. If you have questions, you can type it in the chat you can see in the lower right, and also you'll be able to promote yourself to the podium to ask a question, which we really encourage, just so that we get to see people's faces and hear from them, and or raise your hand. There's all kinds of ways. We welcome any and all mechanisms for participation. So with that, Peng, why don't you go ahead and share your screen? We'll just make sure it's up, and then I'll step down.
Okay.
Great.
Is it sharing?
Yep, we can see it.
And
go ahead, take it away.
Okay, let me get started. All right. So hello, everyone. My name is Peng. I'm a postdoc at the Lawrence Berkeley National Lab, and I'll be presenting our research effort here on the connected economic and environmental assessment of building a circular economy in the US building sector based on CO2 generated products. So as you can see from this title, this is a pretty large topic. Again, I really would like to thank Fernanda for being willing to switch the presentation order with me. So that was really helpful. And so I looked, looking into the building industry to start with, I think a lot of the speakers or audience are pretty familiar with this. There are many stages where a building can emit CO2. So during its construction, the manufacturing of the materials such as concrete, which is made from cement, or the manufacturing of wood, iron steel bars can emit CO2. And when the buildings are built and become in service, there are a lot of energy associated with lighting, heating, cooling, or just a lot of human activities in general has a lot of carbon emissions. And when the building finishes its service, the end of life management, which turns building into construction and demolition debris, also known as CDDs, also emit a certain amount of CO2 as well. So apparently, if we want to look at the potential for environmental improvement in the building industry, we must kind of break down these emissions throughout the different stages. So currently, a lot of research is working on estimating the CO2 emission potential in the building industry while it's in service. And many of them are actually targeting on an international level. So here are some background numbers we pulled from different sources, including journal publications, NGOs, or the United Nations report, and so on. So I'll let you look at these representative numbers for a while. But overall, the idea that we got from all these sources are that the building industry emits a lot of greenhouse gases and is increasing by a lot. However, a lot of the studies are focusing on the international level. So here at the Berkeley Lab, we're looking at the potential of generating a database or report, honestly, to specifically focus on the CO2 emissions associated with different parts of the building sectors, but specifically within the United States. And how do we potentially create a circular economy that could potentially reduce these emissions? So this is a critical important task because actually this problem has been looked at by different agencies and institutions, such as the EIA, the US Energy Information Administration. They indicated that in order to reach net zero, the direct building CO2 emissions needs to fall by 50% by 2030. So now, as you could probably imagine, this is a pretty ambitious task, and you'll see later that a lot of the numbers are focusing on the energy use associated during the building's in-service time, and not many has focused on the construction and so on. And our scope of this study are to see what is the CO2 emission potential within the building industry allocated to different subsectors. So what are the potential of reducing the carbon emission in the building industry using economical methods, but also the methods that has recently been developed that really could includes carbon capture utilization. So right now, we're in the process of building an material IO table, in and out flow table for the different materials used in the building sector, including cement, wood, and other stuff. And based on this, we'll allocate the emission related to these different materials, such as I mentioned, iron, steel, cement, and so on. And eventually, we want to get a sense of the temporal behavior of the potential emissions when you have different materials flowing into the building, and you have different numbers of buildings being built every year. So we're looking to essentially couple this material flow analysis into this study in the future as well. And for this study, we're actually really utilizing data source from different agencies, as many as possible, really, to get a good sense of the materials used in the building industry. So there are some examples of data source we have looked at. For example, we have looked at the Environmental Protection Agency, the Portland Cement Association, the Iron Steel Institute, and many others a lot of you might be familiar with. And while walking through these databases, some challenges we have found so far are that there's limited material flow data within the building sector in the United States. Most of the existing literature is looking at the entire construction industry, which involves buildings, roads, railways, bridges, etc. And we really had to make some assumption to start with to estimate how much is allocated to the building sector based on several representative data we could find. And so yeah, so as you can see in the we have a lot of challenges. So we definitely had to make a lot of assumptions, which makes us in a difficult position where we try to kind of narrow down the ranges, and we're still doing some of that. So you'll see some of the data I'm presenting has a quite large range of numbers. So that's where this is coming from. So here are some representative data we have looked at. For example, the Office of Resource Conservation and Recovery at the Environmental Protection Agency, they publishes the construction and demolition debris management situation in the United States once in a while. And it's really useful in this case because the most recent report just got published in 2020, which looks at the construction and demolition material flow in 2015. Now, because of this report, there are actually a lot of published peer-reviewed journal articles based on the series of report by EPA, which looks at the US construction and demolition debris flow. So this right now is an example published, I think, in Waste Management that built out of the report that looks at the 2014 data. But these data are for construction sector, so we had to dig a little more into it to see how much is actually from the building sector. So aside from the construction demolition debris, the situation on actually the actual construction of the building is different. For material usage during the construction phase, there are reports by USGS or the Portland Cement Association on the approximate consumption of these materials in the building industry. But as you can see from this table, a lot of the numbers are not that up to date, which I kind of mentioned in the previous slide. So there are many different ways we had to do to work around this. For example, using extrapolation from using these data from 1902 to 2002 to kind of assume different growth scenarios and extrapolate this data to get more recent numbers. So after performing these kind of analysis and assigning carbon emission factors to different materials used during constructions and energy consumption for various activities, or some just percentage of carbon emission distribution during the different phases of the building's lifetime from literature, our preliminary analysis shows that there's a general idea of how carbon emission is distributed among the building's lifetime. And now, because I just mentioned, we used a lot of extrapolation of previous data, and there are different literature models for carbon factors from the building information modeling and life cycle assessment. So the range we have right now is a little large, and we're looking to narrow down this range. But mostly the trend is that within the buildings being built in 1 year, let me see if I can get my highlighter or the pen. Within the buildings that's being built within 1 year, the emission really, the distribution of carbon emission is mostly during its operation, followed by its construction. And the construction, the carbon emitted during the demolition process is pretty small. And note that, as I just mentioned, this is only the emission of a building being built within 1 year. So the total building emission during operation, estimated by the US GBC, which is the Green Building Council, I believe, is around 2,000 million metric tons per year. So if we look at it this way, then the lifetime emission of one batch of the buildings, which is the number we have, is around 2,400 to 4,500 million metric tons, falls generally within this range. And also, the lifetime emission number we have here, I would say it's a little conservative because we did not include maintenance and replacement of the building material that's being used throughout this building's life. So even though we're still conducting the material flow analysis to understand the total emission profile, accounting for the new buildings being built every year and the amount that's being serviced each year, one thing we're certain is that we have to reduce emission. So synergistically, we're reviewing the potential of utilizing CO2-based products to reduce the net emission in the building sector for each of these breakdowns. So take the cement or concrete as example. This is a typical breakdown of a concrete made of cement. So it includes aggregates, water, cement, and trapped air that is used to cure the cement. So within the cement industry, there are a lot of the opportunities to utilize CO2 to change this industry. For example, using CO2 as a curing agent, or using mineral carbonation, which involves the reaction of CO2 with industrial waste like iron steel slags to make concrete aggregates. So we have done a thorough lit review in the first half of this year related to some of the emerging studies that came out related to these topics. So I'm going to show you some of the example technologies we have looked at. So these are some examples, so I can go over them fairly quickly. We have looked at CO2-aided curing, so you probably know about Solidia, which is a company developing novel cement materials from CO2, or magnesium-based cement or concrete made from mineral carbonation and CO2 curing that really exhibits similar mechanical strength as the conventional concrete. And these are some just further examples of mineral carbonation, part of which where my previous PI or myself has participated in developing these processes. And besides cement, we also looked into the potential technologies for steel replacement using glass fiber or carbon fiber, or using materials enhanced with the mixing of biochar, which could be used for CO2 capture during the building's in-service time. And this slide really just illustrates that our scope also examines whether a target process is economically beneficial or it's economically feasible based on the techno-economic analysis. So, however, even though all these technologies sound pretty promising, because the manufacturing of these chemicals, even though they're made from CO2 involves process-based carbon emission. So our preliminary analysis results so far shows that they're not really a significant change in terms of net carbon emission from using these CO2-based materials. So if we look at it again, this only shows the buildings being built in 1 year. So we could see a 400 million metric tons of drop in net CO2 emission out of the around, I would say, 4,000 million metric tons throughout this batch, the lifetime emission of this batch of buildings. But again, because we're looking at only the buildings that's been built in 1 year and their net emission throughout their lifetime, say 60 years, if we combine and incorporate material flow analysis to the dynamic amount of buildings built and in service all the time, the potential net savings could be a lot larger. But again, we do encounter a lot of challenges, mostly for the material flow, since a lot of the material usage data is not very up to date, and the reporting frequency varies from agencies to agencies. So it'd be really nice that the United States could have a nationwide reporting system. As much as we realize how important this is, we also think that once we finish building the material in and out flow tables for the building industry, it'll be really helpful for the field. So yeah, I think with this, I'm done, and I would like to end with acknowledging the Department of Energy and Advanced Manufacturing Office for funding this work, and happy to hear about your suggestions on some of the, for example, the database you find beneficial that I'm missing, or any suggestions on where we're going with this, and they will be really helpful for me. Thank you, and I think I'm finished.
Great. Thanks very much, Peng. As I mentioned, we'd love for you to join the podium to ask questions. You can also type them in the group chat or use the question feature. There's all kinds of different options.
Yeah, so I think I cannot see the chat box.
Okay. I'll let you know if something comes
up.
And in the meantime, I'll maybe get started with this. You talked about this being a database, which is great. Tell me a little bit more. Would it be primarily, or it sounds like it's a database that includes material flows and environmental impacts, or would it focus on a bit more one or the other?
Yes. So I think right now we're focusing on the material flow, and for the environmental impact, especially the carbon emission factors, we're mostly relying on the existing life cycle assessment database or published studies regarding, for example, how much CO2 emissions is related to the iron steel production. For example, how much CO2 is related to the the Portland cement production, these kind of things. Right now, we're focusing on the material flow.
Got it. That makes sense. You also mentioned, or like as you said in your title, the idea is this might help a bit with creating more circular economy type flows. What do you think would be ways? So I can imagine how you're doing it on the production side, and then how would it help with kind of circular economy? Would it be waste related things as well, or?
Yes. So one of the things that we found, let me back up a little, is that, yes, so it's not really something we have found, but it's something we found through literature review, is that a lot of because the construction and demolition in the United States, I think EPA was doing a pretty good job at this. They characterized it pretty well in terms of how much construction and demolition debris is going into the next use of the materials. So I think by building a circular economy, we're actually want to kind of quantify how much the material inflow to the building sector is from these construction demolition debris. And because we already found, or other people have found, that the carbon emission related to handling or just the demolition process is really small compared with the actual construction process. So that's why we believe there's a great opportunity for circular economy within the building sector, and that I think that was primarily the reason why I put that in my title.
Great, good. Fernanda, do you want to ask a question? Yeah, please go ahead.
Yes, I do. I don't know if you covered that, and thank you for your presentation. But my Wi-Fi dropped at the beginning, so I'm not sure if you covered that. But did you consider the emissions related to the material replacements and the material flows as well, related to the replacements of these building materials over a building life cycle?
No, I think I mentioned this on this slide. So right now I mentioned that these numbers we have is conservative because we haven't taken into account the replacement so far.
Great, and there's a question in the chat that's kind of about that as well, Fernanda, from Bensu, and wondering if there is much of a study about carbon emissions due to repair and replacement. And so I don't know. I don't know if you're familiar with something specifically on that, or maybe if we can crowdsource that question and see if other folks can put that in the chat as well, if they do know more studies about emissions of repair and replacement. It does seem like something that's been done, but to be honest, off the top of my head, I can't really think of one.
Yeah, same here. I would really appreciate if someone could, help us, direct these sources, because it's something where, as I said, we haven't looked into and we wanted to do.
Great. Xi also has a good question in the chat about whether or not you're considered or are planning to consider future changes in the carbon footprint of building materials, right? So there are roadmaps out there about how to reduce impacts of steel and concrete. And so you didn't mention it, but maybe in the future that might be an interesting thing to include, is how those might evolve over time.
Yes, we're looking into we definitely, the policy related recommendations is something we're hoping to do in the future. Yeah. But right now we're focusing on at least the results or the technologies that has been demonstrated, at least at the bench scale, that are economical.
Yeah. Excellent. All right. Well, thanks very much for your presentation, and thank you for trying to meet both of them. And it looks like Xi already just put in a link in the chat that you can get to about some emissions that he said that includes replacement. So I knew that we could crowdsource it. We're already getting one from Fernanda as well. So take a look at those.
Thank you.
Great. All right. You'll stop sharing and you'll be removed from the podium. There we go. All right, next up we have Rezvan, who's going to be presenting something that's certainly related, looking at material stocks of buildings. And while Rezvan is being promoted to the podium, I just wondered, is Hao Kai or any of his co-authors on here, because that's our last presenter, and I haven't seen him on here. So if you are, then let us know in the chat. Maybe someone else is going to present for him. So, all right, Rezvan, why don't you go ahead and take it away?
Great, thank you. So I just want to make sure everyone can see my screen. Good afternoon, everyone. My name is Rezvan. I'm a PhD student at the University of Pittsburgh, working with Dr. Melissa Bilec. Today, I'm going to present the outcome of our review project on material stock analysis of buildings, and further talk about barriers, opportunities, and future work in this field. So the fast pace of population growth and urbanization has led to significant rise in the amount of materials. And according to the Global Material Resource Outlook, the global material will increase by almost 85% until the year 2060 compared to 2070. And as you can see in this graph here, building materials that are usually found in buildings such as sand and gravel will dominate the resource depletion, especially in future. And in addition to the resource depletion, buildings and construction sector has the highest share of local waste. So according to the data from Environmental Protection Agency, this local waste correlates with the building use type, and also it varies over the different life cycle phases of the building. So as expected, the local waste generated by demolition has higher rate than during the renovation or construction of the building. So with that being said, the materials that are accumulated in existing buildings can be used as a repository or mines for natural resources, and then can be used for new construction, which promotes and improves the circular economy of building sector. So in this project, our goal is to advance the building sector in the context of circular economy through reviewing the existing literature on material stock analysis of buildings. So in order to achieve this goal, the first objective was to understand and characterize the scope, system boundary, and resolution of different articles. Further, we will classify the existing methods and approaches. And finally, I will talk about the barriers or roadblocks that we found regarding the MSA of buildings and opportunities for future work. So we utilized a Scopus database to find relevant articles which were published after the year 2000. So 3 phrases were used as keywords to search the database. And under the criteria of time and these keywords, we found more than 11,000 articles. So through a rigorous process of reviewing the abstract of those articles, we narrowed down our selection into 62 articles, which focuses on the material stock analysis of buildings at a scale. So as you can see in this diagram, as we move forward to recent years, the number of published articles has increased, which show the growing attention toward MSA of buildings. In addition to the number of articles that are published, the trend of studies with more holistic overview of type of materials shows an increasing trend. As you can see in diagram, articles that are published recently, for example, between 2018 and 2021, 85% of them accounted or quantified more than one type of material in an area, whereas previous studies were more focused on just one types of material. So with that being said, we wanted to characterize the different scope, system boundary, and resolution regarding building function, building component, a spatial or geographic boundary of buildings, and the temporal, a spatial or geographic boundary of the articles or studies, and finally, the temporal resolution of different articles. So first, I'm going to start with the building function. The importance of identifying building function is twofold. First, building standards, guidelines, and codes are usually formulated based on building function. So if we classify our building stock according to function, then we can use or extract data and information embedded in those standards and building codes. The second reason for the importance of building function is that building function have impacts on both the composition and the quantity of material. So when we were reviewing all these articles, we found that building function can be categorized into 3 broad categories of residential buildings, non-residential buildings, and buildings that are classified as other. So in this table, you can see the partial list of articles that we reviewed and their categories of building function. So in either of these 2 broad categories, residential and non-residential, we identified some subcategories. 9 subcategories were residential buildings and 19 subcategories under non-residential. However, if you look at the subcategories of non-residential buildings, you can see that there are some overlaps. For example, buildings categorized as economics can also be categorized as institutional buildings or office buildings, but different articles used different terminologies in this regard. So the recommendation here is to use collective or harmonized terminology for building function, which can actually improve the reproducibility of this field. For example, using ISO standards on buildings and civil engineering works vocabulary. The second aspect of characterizing material stock analysis of buildings is building components. So we all know that building materials are either found on in structural components or non-structural components. But the importance is in the end of life of the building components. Selecting end of life strategies, which usually align with circular economy, can be different for structural components or non-structural components. For example, wood that is retrieved from structural components have different obsolescence pathway than wood that is actually retrieved from window frames. However, when we were reviewing the 62 articles, 80% of them did not distinguish the material from structural components and non-structural components. And only 19% of these articles conducted MSA for structural components. So in future, it is important to not only quantify the material, but also specify where these material locates in the building, which actually improves the circular economy and actually facilitate the after-life use of building materials or components. So the third aspect that we were interested in characterizing was a spatial or geographic boundary. So in reviewing the 62 articles, we identified 7 different spatial boundary categories, which are actually sorted in this slide from larger scales to smaller scales. So as you can see in the right-hand side diagram, which is a kind of frequency diagram, most of the articles were conducted at country level or city level. But these were not just the only thing that we were interested regarding the spatial or geographic boundaries. We were also interested in seeing where these material stock analysis studies or articles conducted their research, because the location of materials is also important to facilitate the reuse or recovering of materials and using them in new construction. So we created this map that shows the number of articles for every country. So as you can see, majority of the world or countries in the world lack any studies or research in the material stock analysis of building, which shows a great opportunity for future of this field, and also introducing and proposing new methods and facilitating the conducting the research in this area. So the last aspect of characterizing articles or studies in material stock analysis is temporal resolution. The importance of temporal resolution lies in the fact that it affects the approach or the methods that are used for analyzing accumulated materials. Also, it ties to the goals or purpose of the studies. So the temporal resolution can be classified into a static and dynamic, and the dynamic ones also can be categorized into retrospective studies, prospective studies, and retroprospective studies. So a static studies just pick a slice in a time frame of, for example, 1 year, and quantify and specialize material stock of buildings in that specific time slot. Retrospective studies are more interested into trend of material in buildings from past to present, and retroprospective studies are interested in the same trend, but it starts from past, continues to the present, and also it's projected to the future. Finally, there are dynamic prospective studies that are interested in projecting how the balance of material in the context of their quantity and type and also a spatial distribution will change in future, which are important for most planning and policy making purposes. So with that being said, I want to transition into the methodology or the approaches that are usually used for the material stock analysis of the buildings. The core component of MSA is defining typologies, which are group of buildings that have similar characteristics regarding type and quantity of material. And they are important because we cannot quantify the material of thousands of buildings in an area. We need to have archetypes or typologies that represent that building stock in an area. So the importance of detailed classification and characterization of building typologies is that they improve the accuracy of models, and also it helps the transferability of studies for the future purposes. So reviewing the article shows that 8 categories were mostly used to classify buildings of an area into typologies, which are listed in this frequency diagram here. So as you can see, building function followed by construction period and structural systems are the most popular ones. So buildings typologies are important because material intensity of buildings are determined for every typology, and then that will be scaled up to an urban area or a country area. So the material intensity can be defined as the measure of material that exists per unit of a building. For example, mass per floor area, mass per volume, mass per building. So our intention was to create an inventory, a comprehensive inventory that documents the categories that were utilized to define the typologies, and then the number of typologies for every studies, and how material intensity of those typologies were determined, and also the unit of material study. So this table here shows the kind of partial screenshot of that inventory that we created. Also, we found 4 major methods to determine the material intensity for different typologies, which are consulting with experts or relying on existing literature, such as journal or conference articles. The third major method is building standards or handbooks or manuals. And finally, evaluating sample buildings through on-site inspection of those sample buildings, or digging into architectural documents or material takeoff, or if available, LCA inventories of those sample buildings. So moving from material intensity to general approaches of MSA of buildings, this figure summarizes the proposed approaches by various articles as bottom-up approach, top-down approaches, and remote sensing approaches. Bottom-up approaches can be classified into 4 classes. The first 2 categories are, actually, let me use my pointer here. So the first 2 categories use either the available floor area or the floor area obtained from GIS analysis, then mesh the floor area with material intensity in order to quantify the material. The third bottom-up approach estimate the volume of buildings using GIS analysis and mesh the volume with the material intensity to quantify material. Finally, the element-based bottom-up approaches use surface area or volume of different elements of buildings with their corresponding material intensity in order to quantify the material. I have to say that bottom-up approaches are really beneficial for circular economy purposes because it provides the opportunity for authors to specialize the materials in an area. Top-down approaches are either using import, export, and domestic production data to quantify the material, or using population and floor area per capita meshed with material intensity to quantify the material. Finally, there are few studies that use remote sensing techniques such as night light images or satellite images to quantify the material stock of buildings. So, and I have to say that top-down approaches usually provide the big picture of the material accumulated in the buildings that are usually beneficial for policymaking purposes. So with that being said, we found that lack of databases, especially in regards to geometric properties of buildings, are the first barrier of material stock analysis of building sector. The second barrier is paucity of building typologies and their corresponding material intensity, which is the big portion of conducting material stock analysis. As I mentioned before, one of the barriers are disparate terminology regarding building function, and also not distinguishing between the materials accumulated in different components, such as structural components and non-structural components. So one of the opportunities that can be actually pointed out here is utilizing the existing articles on MSA of buildings to move forward with component-based component stock analysis. Rather than quantifying the materials, we can quantify the components which can be reused directly in new construction. Also, we can use the available geometric data from existing urban building energy models to foster and promote the material stock analysis of buildings. For example, there are urban building energy models in the United States, in Boston, Pittsburgh, Houston, San Francisco, and Los Angeles, that can be used for material stock analysis purposes in the future. So with that being said, I want to thank all the authors and their significant research that inspired us in this review project. And I want to thank you for your time and attention. And I will be happy to answer any question.
All right, great presentation. Thank you very much. As you know, everyone, feel free to promote yourself to the podium. We'd love to see you and hear from you to make it seem like we're really together in person. But you can also type something in the chat or raise your hand or use the question feature. You know what's, oh, great, here we go. Yeah, please go ahead.
Hello. Thank you, Rezvan, for the presentation. You really did summarize a lot of work, so it was really great. Can you comment on how far behind the US is compared to the EU? Because you showed the map, and in that map, we couldn't see that much of studies from the US. So I was wondering if there are, any space of improvements comparing to EU.
Yeah, so for example, in some European countries, like for example, in Germany, I think there are 5 studies that conducted material stock analysis of buildings. And in the United States, we only have 3 studies so far. But I think the challenge is regarding the databases because it's really hard to conduct MSA without the appropriate data. So we have to go back and build the databases first and then conduct the MSA. I don't know how far it's behind the EU, but I hope we are actually moving forward with it and doing more research in this area.
Great, thank you.
Great. There's a good question in the chat. Do you see it there, Rezvan, from Aldrich, or do you want me to read it?
Yeah, I can see that.
Okay.
Have you?
It's basically about a meta-analysis of material stocks across existing studies, which is an interesting idea. So,
Yes, I think, thank you for this question. No, we haven't actually conducted a meta-analysis, but this is very an interesting kind of suggestion or recommendation. Yeah, we will consider it for future.
Great. Yeah, great. Fernanda, go right ahead.
Yes, thank you, Rezvan, for your presentation. Can you tell us a little bit of like why it is important to do a component stock analysis in addition to material stock analysis, and how that would improve the circular economy of buildings?
Yes, thank you for your question. Talking to companies that are actually working for the, improving the end of life of building materials or building components, we realize that they are more interested in the components that can be retrieved after demolition of the building. And also from the point of view of circular economy, when we demolish a building and use the material is usually downgraded. For example, crushed into stone. So it usually does not preserve the value, the initial value of the material. So it is kind of important and interesting to kind of conduct the component-based analysis to see the quantity and type of component that can be salvaged from the existing buildings and used in the new construction.
Great. All right. Well, this is clearly, I think you have a lot of votes for people that this is a useful work that you've done to kind of compile all this information together. And now you also have some ideas for what to do next as well, if you didn't already have them. So I'd say that's a successful conference presentation. So thanks very much, Rezvan. We appreciate that.
Thank you.
And looks like make sure to check in the chat. Xi just gave you a good recommendation for a paper as well. So.
Sure, thank you.
All right, let's bring Fernanda back up to the stage here to give her presentation. In case you missed at the beginning, we had Peng go first because he was going to present somewhere else at the same time right now. So Fernanda is up to talk about building design in the U.S., circular building design. So go ahead and I'll let you know when it's up. Sure, yeah, that's okay.
Can you see, okay. Can you see that okay? Oh, I can't hear anyone.
Sorry. When you were there. What happens is I was just taken off the stage when you were there, and so then you don't hear me. But everything you did was correct.
Okay, so I'll do it again. Sorry.
But I'll try to stay on here to make sure that great. See it, and it's in. All right, go right ahead. Please do.
Okay, thank you. So good afternoon, everyone. My name is Fernanda Cruz Rios. I'm a postdoc at the University of Pittsburgh, and I work with Dr. Melissa Bilec in circular economy in the built environment. I also work with Rezvan. And today I'm going to present the results of an empirical study we did in which we interviewed architects in the United States to identify the barriers and enablers to circular building design. So the built environment uses almost half of all the materials extracted every year in the world. And according to a recent report from the Ellen MacArthur Foundation that you can see here in this figure, the circular scenarios for the built environment can reduce carbon emissions by 38% in 2050, or even 56% beyond 2050. And here are some of the scenarios that they consider for this projection. So first, eliminating waste from building design by using resource efficiency measures like, for example, avoiding over-designing structures. Eliminating waste in construction through strategies like prefabrication, off-site construction, and 3D printing. Sorry about that. Sharing business models like peer-to-peer renting, office sharing, and multi-purpose buildings to increase their utilization rates and better use the building space. Also prolonging lifetimes, so maintaining the economic value of a building over time through modular, flexible, and durable design. And finally, reusing building materials and recycling them when they cannot be reused anymore. So in theory, all of these scenarios can be partially enabled by design for disassembly or design for deconstruction, how it's often called in the built environment. So the deconstruction of buildings as opposed to demolition is not uncommon, especially for historical buildings that have valuable materials like reclaimed wood. But one of the main challenges of deconstruction today is that the buildings were not designed to be taken apart. So design for deconstruction is the act of designing a building to make it easier to take it apart in the future. And this future can be either like a short-term future, like a partial deconstruction for building renovations, or long-term, like a complete deconstruction instead of the demolition. 1 second, I think I have like an automatic, I don't even remember how to, anyway, I don't remember how to do that if anyone does. But it's just shifting automatic. Can I leave my screen like this? Is it okay? I'll just assume it is and keep going. Let me go back here. Sorry. So some key principles of design for deconstruction are using fewer materials, using modular and prefabricated elements with standard dimensions, designing flexible spaces that can be adaptable to future building demands, providing a deconstruction plan, and also like labeling the building components, and designing with durable components that are mechanically connected. So for example, using screws or instead of welding or adhesives. And there are very few examples in the world of non-temporary buildings that have been designed for deconstruction. And when I say non-temporary, I mean buildings that are designed to last anywhere from a few decades to a few hundred decades in their site. So that does not include buildings that were designed for specific events, like expos, for example, and buildings that are designed to be taken apart or relocated in the very short future. And one example in the United States is the Bilec Center in Seattle. It was designed to deconstruction. So this building, one of the key drivers for this kind of design for deconstruction was that the building could last longer by adapting to future demands. So for example, if the facade needs to be changed in the future for any reason, it all comes apart from the core structure. So we don't need to demolish the whole building. So recently, some studies have investigated the barriers for design for disassembly and reuse in the building sector. And these studies are listed here in this table in the left, but only 4 of them, they marked as yellow, only 4 of them were empirical. So the authors collected data from stakeholders. For the rest of them, the data was collected from the literature. So all the empirical studies were conducted in European countries. And they used methods like surveys and interviews in different samples of construction stakeholders like architects, engineers, consultants, and contractors. So there are several types of barriers that were identified in these 10 studies. And these types of barriers are here in the right. So for example, technical barriers are related to design, manufacturing, and construction. Technological barriers include challenges related to technology and infrastructure. Cultural barriers include cultural, social, and behavioral aspects. Educational barriers are related to stakeholder awareness, knowledge, and skills. Environmental barriers include environmental impact metrics and reduction strategies. Regulatory barriers include, regulations, code standards, and contractual issues. And finally, economic barriers are related to issues of markets and costs. So from the barriers found in the literature, it was clear that strategies like design for deconstruction would not grow in the construction sector unless the body of knowledge available becomes less fragmented and actually able to guide construction stakeholders on taking these progressive steps towards circular economy. And that is especially true for countries like the US, because we lack here a circular economy specific legislation and educational campaigns. And the progress to our circular economy here depends on bottom-up efforts from construction stakeholders. And yet we did not find any studies that were investigating the barriers and enablers as perceived by these US stakeholders. So in our study, we asked, what are the systemic barriers for circular building design in the US as perceived by architects? And how do these barriers and their types or categories differ from those found in the European countries? And what are potential enablers for these barriers as well? So to answer these questions, we interviewed 13 architects randomly selected from the design firms with the largest revenue in the US. They had an average of 26 years of experience, and we did not require any previous experience with circular building design. We asked them about the design process, what were the client's drivers for sustainable design, also about specific design strategies like using demountable joints, using salvaged building components, using modular and prefabricated building components as well. And at the end, we asked them about their perception about design for the construction. So these interviews were conducted by phone. They lasted an average of 40 minutes. As you can see in this map, they were fairly distributed across the country. And most of them had experience designing buildings for the institutional sector, as you can see in this table, although they did design for several other sectors as well. So after we conducted these interviews, we identified and categorized the barriers existing in the literature according to their type, like I've mentioned before. So then we did a thematic analysis in our transcripts to identify the similarities and the differences with the literature. So from this analysis, we identified new barriers to the literature, the most mentioned barriers as well, a few potential enablers that emerged from our data, in the number of barriers per type that we then compared to the empirical studies in the European countries. Then we propose more potential enablers for each barriers based on our experience. And here I need to mention that the co-authors and I have been involved in important circular economy discussions recently. Dr. Bilec and I are working together in an NSF grant called Convergence Around the Circular Economy. And we have discussed these barriers and enablers in different sectors with scholars from different disciplines, from like anthropologists to chemists, and also with industry stakeholders. And we also organize a workshop called Designing for Circular Economy, from Molecules to the Built Environment, where we discussed several barriers and enablers with circular economy experts around the world. So here's an example of our process and findings for one of these types of barriers, which is technical barriers. So here in this table, articles 1 to 10 are the articles that were mentioned before in that table that I've shown before. And number 11 is this study, like our interviews. So here we can see from our barrier inventory, which ones we also found in our data, and then the barriers that were new to the literature at the bottom here. So for example, one participant mentioned that there were conflicting goals between pre-engineered structures and future reuse. So for example, when you optimize the design of a structural component to a certain load, you use fewer materials, so you're doing a resource efficient strategy, but you make it harder to reuse that in the future. And another participant mentioned that what he called like a Walmart effect here in the US, which is he described as a continuous drive to make things as inexpensive and non-durable as possible. In total, we identified 10 barriers that were new to the literature. And of course, we don't have time to go through all of them, but I've highlighted here an interesting example. There was a cultural barrier that was both new to the literature and one of the most mentioned by the participants. And it's the belief that design for the construction compromises building durability and resilience. So in other words, the architects think that buildings that are supposed to last for more than 100 years, like institutional buildings, for example, they need to have strong and resilient structures, and that does not lend itself to the construction. So they perceive resilience and as strength and toughness as opposed to flexibility and adaptability. In comparing the types of barriers with the European studies, we found that here we had a larger share of educational, cultural, economic, and technical barriers, and a smaller share of regulatory and technological barriers. So there can be a few different explanations for these differences. For example, the participant samples varied across the studies. So we in our study only interviewed architects, while a couple of other studies used a similar sample size, but they used a mix of different stakeholders. And the data collection methods also varied from surveys to focus groups to interviews. But another possible explanation for these differences is that we have a different regulatory, economic, cultural, and educational context here as opposed to compared to European countries. So for example, in Europe, we have the Circular Economy Action Plan. We have the Ellen MacArthur Foundation and European green building rating systems that have contributed to raise awareness and knowledge around circular economy for the past few years. And finally, some barriers that are found in Europe may be enablers in the United States and vice versa. So for example, storing salvaged materials in European countries is often cost prohibitive because they don't have enough land to store it. But here we have a larger availability of land in the US, which means that we have more opportunities for accommodating the storage infrastructure, which is likely to result in more economic storage solutions for salvaged materials. And we also identified several enablers that could help overcome a range of barriers, and the stakeholders that would be responsible for creating each enabler. So for example, NGOs, professional associations, and universities could help raise awareness on circular economy. Building designers could try to sell design for the construction as a means to increase buildings' adaptability and resilience, so educating building owners on that. Researchers could create database for reusable building components and study the existing material stocks like Rezvan's work. And policymakers can create fiscal incentives for circular economy strategies. So this figure here shows how many of these enablers that we identified would fall into each stakeholder. Of course, this is an approximation, does not mean to be comprehensive, but it was interesting to notice that most enablers that we found that would help overcome the barriers could be put in place by policymakers. And these regulatory enablers could help overcome a variety of barriers, from educational to cultural to technical barriers. So if you're interested to see the whole picture, we do have an article in press in the Journal of Construction Engineering and Management, where you can find a more detailed list of all the enablers, which barriers they address, and the respective stakeholders that would help put them in place. And in conclusion, to make circular economy possible in the built environment, we need both top-down and bottom-up enablers. And to blend these top-down and bottom-up enablers, we need to create opportunities to have a variety of stakeholders at the table early on. And this is true for both industry and academia. So for example, in industry, we can encourage project delivery methods where you can have consultants from several disciplines on board from early design stages. And in academia, we need more convergence research to create enablers to the several different types of barriers that we mentioned. So that means that we must understand that designers and engineers cannot do it alone. And there are important cultural and economical barriers to have overcome. So we need to include disciplines like political science, economics, and behavioral sciences in the discussion. And finally, we need to understand that circular built environment is a complex system. And these barriers and enablers, they are interconnected. And we have to understand these connections and what are the systemic, economic, environmental, and societal consequences for buildings and cities. Thank you. That's what I had. And I don't know how to stop sharing now. Oh, I see it.
All right. Thanks very much, Fernanda. Great work. As always, we invite people to come up to the podium to ask their questions or to write them in the chat there. You've given us a lot to think about, and certainly that's a good example where having the paper will really help us because there's so much content there. Do you guys also get into the paper a little bit about, you know, some suggestions on how to overcome some of the barriers and challenges? And did you want to emphasize or highlight a few of those, if so?
Yes, for sure. So we have I can share again, can I?
Yeah.
Let me see. We have in this slide here several. So this slide is only about these enablers that we proposed, and some of these enablers They emerged from our data, from the interviews, but others we came up according to our experience in circular economy as well. So some of them that I did not mention include, for example, university leaders. They can integrate circular economy into the university curriculum in all sectors, so that can facilitate multidisciplinary discussions. Contractors could offer contractor warranties on the quality and safety of salvage components, and that's key because there's a huge lack of trust when architects try to procure salvage materials. It's more like treasure hunting for them. So there's a bunch of other enablers. I could talk about this all day. I hope I gave some examples.
Yeah. Great. All right. Looks like we got. Oh, Federica, did you want to ask a question? Unfortunately, we're having trouble hearing you. You want to try again? Yeah, it doesn't seem to be working. Do you want instead to, like I said, normally I would be delighted to have you talk, but let's try it one more time. Now we can see you. That's good, but it's still pretty quiet.
Maybe now.
Okay, yeah, there we go.
Okay, I had to change the microphone. Sorry for the trouble.
That's all right. That's good. Like I said, I'd rather hear it from you than have you type it. So please go ahead.
Yeah. So thank you for the presentation, Fernanda. And I had just a question about if we start to actually employ this method and design for disassembly. What's the extent of the research until today about re-employment of structural materials? Because maybe for finishings, it's something that somehow we have the knowledge to start doing it right now, but for structural materials, what we can actually do?
That is a great question, Federica. I have seen a couple of very recent studies showing and I can look for them and put them in the chat. But one of them shows they did a test with structural steel. I think it was steel. So with structural connections of steel that were bolted and how they resisted to seismic loads, how they performed under different structural scenarios. And they found that they were able to meet. They had a slight decrease in their structural properties, but they were still able to meet the minimum requirement for that structure. So that was good. And yes, we are just starting now to have more research on the area as well.
Thank you.
Yeah, that's great. There's also a lot of discussion about that with wood. I know a lot of people say that structural wood, it's even stronger than original wood, but still people who specify it are hesitant. So it's a really good point. And Melissa asked a question about what engineers might think, and I think that's probably a lot of what they'll be talking about as well. So
what they might think of the overall. One thing that I don't know about engineers. I think when you said engineers, I first thought about contractors. So I'm in the wrong side. But I would say construction stakeholders in general. I think we have a cultural problem, which is it's a risk-averse sector, right? Mm-hmm. So we are in that mindset of we've been doing that for so long, and why do we have to change now? But there's a few major confusions, and one of them is what is circular economy, and what is it? How is it even different than sustainability? And why do they have to go an extra mile for that? That is something that comes out a lot, and this is something that we are all figuring out as a community, I think.
Yeah.
And another thing is one thing that I hear a lot is I heard from an engineering reviewer once was so the design for the construction is not the only reason why we don't deconstruct buildings. Is the buildings get obsolete and demolished for other reasons, their economic life was over. They don't make more sense economically anymore. It was there's behavioral barriers, and I was yes, this is all true. But if we solve all of this and do not design for the construction, we still cannot salvage these building materials in conditions like Rezvan was saying before. They're usually downcycled right now. We are not able to keep the economic value of these materials because we don't have the right design practices. And it's going to take a major cultural shift, I think, to change our mindset in construction for that, I'm sure.
Great. Sorry, Rezvan, I appreciate you coming up, but I think we're going to have to switch to the next speaker now. So sorry for that, but thank you very much, Fernanda. You'll see that Aldrich has another question in the chat that maybe you can answer when you're done here. And so thanks very much. We appreciate that. We'll ask our last speaker to come up now, Xinyi, who has a whole bunch of colleagues that have been working on an LCA of residential buildings and looking at targets to net zero. Okay, great. We can see you.
Hi, can you guys hear me?
Yes, see and hear you. It's great. So please go ahead and share your screen. Yeah.
Share.
Yes, we can see it perfectly. Yeah, please take it away.
Sure. Thank you. And good afternoon, everyone. My name is Xinyi. I'm from the System Assessment Center of Argonne National Lab. It is my great honor to speak here on behalf of our team and to introduce our recent study on the life cycle analysis of a residential house using our GREED LCA model. To start with, let me talk a little bit more about the embodied and operational carbon emissions of the buildings that I believe the audience is already familiar with. So, as some of the presenters mentioned, according to EIA, residential and commercial buildings consumed 75% of retail electricity last year. Apparently, we all know there was a huge impact of COVID, especially to the industrial and transportation sectors. But we should still recognize that our buildings are key energy consumers. And as for the emissions, we can see the pre-COVID data showed 28% of global energy-related carbon emissions was from building operational phase, and 11% was from manufacturing of building components and construction, also known as the embodied carbon here. So clearly, as it has been emphasized by many presenters today, the decarbonization of buildings must play a key role in developing a sustainable future. And that is why we have been going through an ongoing effort from our center to expand our greenhouse gases, regulated emissions, and energy use in technologies, or the GREED model, to develop a new building LCA module. The module leveraged the existing process level data from GREED built in the past decades and has the ability to analyze building components and whole buildings. And here's a screenshot of the user-friendly page of our GREED building LCA module. So this module is to be released hopefully in the fall. And for this study specifically, we used this beta version to do the LCA modeling. The inventory data for embodied carbon emissions is collected from multiple data sources such as GREED, research papers, industry reports, or EPDs. And the operational data is collected from 3 houses of similar sizes in the same area. So, because of the importance of understanding building energy and emissions, we utilized the GREED module to do this analysis. The study home is a 2-story single-family home in the greater Chicago area, and that house was built last year, so it's super new. And we would like to discuss key drivers and potential trade-off between the embodied and operational emissions. So now a little bit closer look at the house. Sorry. From the view of materials, we can see that concrete is the dominant material used in terms of volume, and it is followed by multiple insulation materials such as cellulose, spray foam, and EPS. And for the sake of time, we would not show the details of data sources or modeling methodology. So let's jump to some preliminary results directly. From the upper left pie chart, we can see that if divided by material categories, concrete is the absolute dominant part. At the same time, we can see that concrete accounts for over 90% of the total mass from the pie chart on the lower left. If we take a closer look and look at embodied carbon emissions by specific materials here in the right, in a column plot on the right side, we can see the key contributors to embodied carbon emissions are namely concrete, steel, the one dominant part, and then followed by some steels and some wood parts. And we also did a calculation on the embodied carbon emissions per unit mass, and we can see that on average, steel products as a whole category become the leading emitter. And if you look at the specific materials instead of the categories, we can see the plot below that sulfate, which is made from aluminum in this case, is the single material with the hugest embodied carbon emissions per unit mass. And that is for embodied carbon emissions. And if we look at the operational phase or the building use phase, our studied home consumed much less operational energy than the benchmark. We can see that from here, from the right side. And also, if we look at the share between electricity and gas, we can see our house actually has a slightly higher share of natural gas. And for emissions during the use phase, we estimated the greenhouse gas emission intensities of natural gas and electricity in the state of Illinois, again using GREAT. GREAT 2020 is, by the way, the newest version right now. And since you guys can see on the upper right side, the state of Illinois' generation mix has a very high share of nuclear power, which is actually the highest in the whole country. So that the result, the electricity emission intensities is much lower than the US average. And so these are the values we used. And by the way, we estimated both the studied house and the benchmark using the same intensities to be consistent and comparable. So as for the results, compared to the benchmark, we can see our studied house has a much lower operational greenhouse gas emissions. Then we conducted a payback analysis. The plot on the top shows the impact of building service life on amortized yearly emissions. This is also something we are interested in learning more in our ongoing building LCA effort. So to explore a better method to estimate the service life of buildings as well as the building components, and also to see how these service life differences affect the embodied and operational energy and emissions of buildings. And at the bottom, we can see that for this specific house, it takes about 15 years to pay back the embodied greenhouse gas emissions by saving emissions during the operational phase. So comparing to the typical service life of a house, 15 years is not that long, but it is still like not a short term of time. Okay, so to wrap up, here are some take-home messages. First, concrete is a major contributor of embodied carbon emissions due to its high share of mass in the bill of materials. And in the use phase, the studied house has the annual greenhouse gas emissions of 6,800 kilograms, which is 44% lower than benchmark. Also, the house has a payback period of 15 years between the embodied emissions and saved operational emissions. Okay, that is what I have. And again, it is my pleasure to present our work. And please let me know if you have any questions or comments. Thank you.
Great. Thank you very much. Excellent job staying on time and everything. So as we've done before, please jump up to the podium to ask questions or drop them in the chat. I can start out. That payback period calculation was interesting. I just want to make sure I understood it. You had like operational energy saved.
Yes.
Yes.
And is the embodied also like then the additional amount, or that was total embodied for that building? You know what I mean?
Yeah, that is a really great question. And the thing we did is the saved operational greenhouse gas emissions, which is the difference between the study house and the benchmark compared to the study house embodied carbon emissions. And the reason why we did that is that we can't really find a very good source of benchmark for embodied carbon, especially for a single family house. We did find some for another study we are working on that is for a commercial building. But for single family homes, it's kind of hard. So so that is why we defined it as paying back the embodied carbon by saved operational emissions.
Sure. But the embodied, the number you have is total amount of embodied emissions for that building?
Yes.
Okay. Because you might even say, like, frame it as also the difference in embodied. And I just say that because it's like, how much are you investing additional to then save compared to it? So it would certainly be a shorter payback period.
Yeah, that would be.
It's another way to think about it, but that's great. I also, I did not think you could be using GREET on buildings, right? I always associate it with vehicles and fuels, so it's great that you can expand it now to do buildings.
Yeah, that's a new effort, I think started last year, maybe. So yeah, I think in the latest version of GREET, we don't really have buildings yet, but I think later this year, we're gonna release a building module. And GREET is gonna be able to do building analysis as well.
Excellent. Other questions or comments? Okay, yeah, we have a question that just came in the chat. It's sort of a theme. Can you read it? You want me to ask it or?
Yeah, I can see that.
Okay.
Does the
why don't you go ahead and read it out loud in case other people haven't seen it? So.
Okay, sure. It said, does the embodied carbon include the recurring embodied carbon due to renovation and maintenance? And the answer is no. And that is also something we are working on. So we have collected some information on the service life of different building components, and to see if we can incorporate the replacement and maintenance into this analysis. And the short answer is no.
Great. Well, that's a running theme in our chat. In fact, if you scroll back up through this one, you'll see a few recommendations of papers about that. Maybe you heard I said, it seems like that's something that people have done, but we couldn't remember it. So there's some good recommendations in the chat to be able to capture that.
Cool. Yeah, that would be great.
Yeah. Other questions or comments or? Well, thank you very much. This is great work, and we look forward to seeing what comes out of the work that you're doing and the components and GREET that will definitely help to expand our knowledge base and data in this space.
Thank you.
Yeah, thank you. All right, so that's our last talk here. Once again, thanks to all of our presenters for presenting and also for helping us stay on time. We're even done a few minutes early. Just as a reminder, the two things that I shared before, there's a poster session that's coming up at 4 o'clock that Derek has worked hard to organize, and there's a lot of great work. And I think that'll be a good way to sort of test out this platform, be able to hang out with people and chat with them, and do some smaller group video talk, so try that. And then also tomorrow at 2 p.m., like I said, I really recommend joining the Picture a Scientist film discussion that we're going to have at a great panel on that, and those are Eastern time. So, all right. Well, thanks very much, everyone, and I'll see you around at the rest of the conference.